In section 4.3 in the book, the author discusses the relationship of metals in the soil and acid rain and the effect that acid rain has on the metal content in the soil. So we start out by just looking at potassium in particular. Potassium is a nutrient, a metal, particularly important to agriculture and to plants. So most of the removal of potassium from the soil is done by plants through agriculture. So we need to make sure we maintain the level of potassium in soil via fertilizers. So that's the major source of potassium coming into our soil. Now once it gets into the soil, you have a certain amount that's water soluble, and don't worry about the percents on here. Those percents refer to something in the original paper, Heinz and Reinhardt, 93. So don't worry about the percentages, just the flow of the potassium here. So we're starting out with potassium, which we know is a group 1A element. So we know that that is going to be a water-soluble element in that form, in the salt form. So there's a certain amount of potassium that is readily available to plants. It may be adsorbed. Okay, so now that's different from absorbed. That's adsorbed onto the surface of clay minerals. There it is readily available. It can easily be pulled back out again for use by plants. Or some of it will eventually get bound into the interlayers of clay. So in the interstices of the clay, so the inner layer known as potash for clay minerals, that tends to bind the potassium and take it out of service at a little bit larger amount. That's kind of what the percents refer to. But you can eventually pull that back out. You also get a source of potassium not only from fertilizers, but from minerals that are already in the soil that can leach potassium from those minerals via weathering and then make that available for uptake by plants. Now, a certain amount of potassium also is going to get washed out and put into the water system, taken out of the soil system. So what you can see here is that potassium minerals is only very slightly available to plants. Anything that's water soluble is directly available, adsorbed onto the surface of clay. That's our storage point. That's our most important storage point. So there's high availability to plants, but it's something to hold it there in the soil and keep it there. And then the binding, once it's bound, very little available after exchanging potassium once you've kind of reached an equilibrium there. So there's potassium. Now, in this section, the author is just kind of mentioning the balance of not only potassium, but all the heavy metals that we have in soil. So these are going to be things like lead, cadmium, molybdenum. There's a lot of different trace metals that are going to be in the soil. Not all of them harmful. Many of them are important micronutrients, such as molybdenum, very important for plant growth. But there has to be a balance of those in the upper soil layer. And so this is just sort of the formula that shows that balance. So you see all these J's. So the overall balance J is JA plus B plus S plus F plus M minus P, E, and V, where basically all the pluses are things that are putting metals into the soil, things like biocides. And these are insecticides, herbicides, any sort of material that we're putting on plants for a variety of reasons that may release those metals into the soil. There can be metals in the dust that get pulled out by the rain, so that's atmospheric. So that's what the A is for. Manure and fertilizer put those metals into the soil. Treated sludge will put them in there. Now, those are the input sources. Those are the things putting metals into the soil. Things that are taking metals out of the soil. Plants are pretty good bioremediators. Certain plants do a very good job of uptaking different metals. It can work its way down into the soil layers, so deep into the soil it can get locked up, or it can be eroded away into the water system, which removes it from the soil. So that is how we describe the balance of metals in our soil layer. Now, if we look at particular metals, if we look at things that we mentioned. So micronutrients that we need, such as manganese, small amount of copper, zinc is an important one, molybdenum is important, and then things we don't want as much of, things like lead and cadmium. We can see that there's a relationship between the pH of the soil and the uptake of metals. So other than molybdenum, molybdenum's kind of an odd man out here. It's a little bit of a weird case, but all the rest of them, you can see that as the pH becomes less acidic, it is less bioavailable. It's less available to the plants. And these are all levels that are in clover, which is a nitrogen fixing plant. Okay. And so we can see how clover does at taking that up. Now that's just an example. You could make a profile for any plant you wanted, but we're just going to look at it for clover in this case as sort of an example. And now something they don't have on here, but one that is noted in the book that's kind of interesting is the case of aluminum. So if you have aluminum in the soil, small amounts are needed, but the more acidic the soil, the more bioavailable that aluminum will be, and it tends to be toxic to a lot of plants. So many of our what we consider useful plants won't grow in fairly acidic soil, pH of less than about 5.5, because they just end up getting too much aluminum. And there's a really classic case of that here in Southwest Missouri, actually, and this one has been noted nationwide amongst people who study, plants and environmental studies. There's a place called Buzzard's Roost that's in Southwest Missouri that there's a bluff, and on that bluff are growing red oak trees. Now, if you're familiar with red oaks, you know that they get fairly large. They can get 20 to 50 feet tall. The oak trees on this bluff are fully grown, and they're only about 3 or 4 feet high. These are full-grown trees. They're pygmy oaks, and the reason for that is apparently a very acidic soil. The soil there has a pH of about 4.6 and a very high aluminum content. There's an aluminum content of about 600 parts per million in the soil there, and that aluminum uptake was enough to stunt the growth of these trees. They just weren't able to get any bigger than about 3 or 4 feet. So it's a very classic example of how those different metals can affect plant growth. Now, another thing to be concerned about, not only those heavy metals that we're worried about, but even some metals that are very common in the environment. You can always have too much of a good thing. So even though plants need a certain amount of sodium uptake for good health, that you can get too much of that. And one of the ways that we've been putting too much out there is basically salt transport. So when you have icy conditions and you're putting salt out to try to relieve the icy conditions, and you can imagine, again, the author is German, so in Germany there's probably a fair amount of that, but we see plenty of that here in the US as well. Even here in Missouri, that's very typical. If there's any sort of ice, they go out and they salt the roads. Well, what happens is that first of all, that salt can go into the soil from surface runoff. Of course, it is soluble, so you end up with sodium chloride ions in the soil. You can also get those ions airborne through drifting, through spray off the wheels of cars, through drizzle, so it gets picked up into this fine mist. And then that ends up coating the trees and plants that are in that area, especially along roadways. And what you start to see is a lot of issue with those plants because of that increased amount of salt. We see things like, well, first of all, sodium is required by plants to help maintain osmotic ratios, to help maintain their osmotic pressure, to help them get fluids moving through the tree where they need to be. But what happens is, first of all, chloride tends to be toxic to plants, fairly toxic. So the chloride from the salt creates all sorts of issues for the plant. The sodium, even though it needs a certain amount of sodium, it's just too much of a good thing. So when you have too much sodium, it starts exchanging and replacing ions that the plant does need, such as potassium, calcium, magnesium, so on and so forth. It's the same principle that works in a home water softener, that when you want to recharge the softener, you flood it with sodium ions to push out the other ions. And that's the same thing that's happening to the tree. There's so much sodium, it's just flushing out the other ions. They just can't compete with that much sodium. So you end up with nutrient deficiencies. You end up with a tree that is unable to respire properly. It's unable to take up soil air. So they actually do take some gases through the roots, through the soil. The salt also affects, water flow as you get up into the branches and up into the leaves as you go up into the tree. Leaves, it moves all the way out. You'll start to see accumulations of salts in leaf edges and shoot tips, so you'll start seeing different effects in those. You'll see curling, or you'll see yellowing or something from that excess sodium that you've got in your trees and your plants. Now, lead, we know, is a very important heavy metal to monitor in the environment, and that's because of its toxicity. Its toxicity to humans, its toxicity to plants. It's just generally not something we want to have a lot of in our soils, in our air, in our water. So if we look at the transportation pathways for lead, those are pretty standard. We know those. Cars, and those aren't nearly as bad as they used to be, but there's still a little bit of lead emission there. When we had the leaded fuels, we had lead as a fuel additive starting back in the 70s or so. It became a huge issue, the amount of lead that was building up in plants and soils and things around major roadways and major highways. But the problem isn't just limited to those roadways, because that lead from cars, lead from factories, any sort of output ends up getting put into the atmosphere, and then those can be carried for long distances through cloud movements. So lead ends up coming out all over the place, not just at the source of its emission. Wastewater, if it doesn't get pulled out of the wastewater, if it's not treated properly, ends up getting into our reservoir systems, gets into our groundwater, uptake by vegetation, trapped in the soil. And also, here's another source, waste. So when we have lead batteries, things like that get dumped, that eventually migrates into the groundwater. And so we just end up with these sinks of lead. Now, as I said, we have gotten better about that. So if we look at lead emissions in airborne particles, so I know we're talking about soil in this chapter, but if we look at the amount of lead in air, so if we go back to 74, in mid-70s here, that's about where we had the peak of lead emissions. So I know this may not sound like a lot, but this is micrograms of lead per cubic meter of air, and that's actually up here at about 1.1, 1.2 micrograms per cubic meter. That's pretty high. So you can see here your threshold values. Here's what you're aiming for, and then here's the sort of emission, and precipitation that we have going on. So you can see that what we're aiming for is pretty low. What we've actually got is a little bit high, well, quite a bit high compared to what we're aiming for. But you can see that once we knew about the problem, started removing lead additives from gasoline, started controlling emissions from different sorts of industries and plants, you can see that it's more or less dropped off at a steady rate. And this only goes out to 1990. The book's a little bit older, but if you continue going, you'll see that it's pretty much leveled out. We're not down to zero yet, but it has leveled out to more manageable levels. Now, the author addresses the frequency of lead and also cadmium. Cadmium's another heavy metal that can be an issue. Tends to be found in much smaller quantities than we find lead, but still an issue and still a byproduct of a lot of industries. And he looks in particular at the buildup of these materials in garden soils. When we say garden soil, we're talking about someone's backyard garden as opposed to a large agricultural area. So garden soils in particular will show up different than the large agricultural scale. First of all, because it's a more confined area, it's a smaller area. And second, there isn't as much mitigation going on in that soil. There's not as much tilling and working of the soil. So you might till the soil, but you're not going to as deep a level. Crops do not tend to be as intensive on those. You're not putting the same materials on. You might be spot spraying, so you might be getting small local areas of concentration. And it's just a different soil profile. So when we look at those, in the left side here, we see garden soil that has deposits from mining industry. So these are in areas that have lots of mines. This you wouldn't see quite as much around the Springfield area, but this might be more representative of what you might see in Joplin, where there are old mines, in particular lead mines. So you can see for lead and cadmium, and then you can see for areas that don't have material-specific deposits. And so you can see that when you look at the size fraction, when it says frequency distribution, what we're looking at here is the range of the soil here, milligrams per kilogram, so particle size kind of, and then the percent of that element in there. And so you can see how, there's a slightly different profile, but it varies from mining industries, and then ones where it's more generalized, where you've had this spread. This slide is an interesting look at how different metals in soil can be monitored using standardized levels. So this is standardized lead levels. So for those of you who have had quant, you may have seen this already, or if you've had the analytical methods for the lab tech program, you may have seen internal standards used. And that's sort of the same idea that is being used here. So this chart is indicating looking at lead levels from some sort of emission source, from an emitter. In this case, some sort of a factory that may be emitting lead. And so the thing is that while lead is being emitted by this factory, there are other sources of lead that also produce some sort of background level in the soil. So how do you know if the lead is coming from the emission source or if it's coming from some other source? So in this case, the burning of coal, which across Europe is not a point source. Everyone's using the coal. So how do you know if you're looking at lead coming from your emission source? So what they've done here is they've coupled the lead with another element that is only being produced by the emitter, vanadium. So vanadium is also coming out of this plant. So we have lead and vanadium, but vanadium is not something you're going to see from the burning of coal. So if you look on here, the green line indicates the levels of vanadium in the soil at a distance from the point source. So our x-axis is kilometers away from our emission source, and our y-axis is the amount of element that we have in here, milligrams per kilogram of either the vanadium or the lead. Okay, so the blue line is the lead. And so you can look at that and you can see that the vanadium stays more or less steady up to a certain point in here. And then the lead, we're seeing a spike. So what they've done is taken the ratio of that. So the amount of lead that you have minus the amount of vanadium, and then take the ratio of that to the amount of vanadium times 100 gives you your internal standard. And so you can see that kicking in right here, at about 12.5 or 13 kilometers, we start to see this spike. We get a change in the inflection, and we see a spike in the amount of lead. That is the lead coming from the emitter. So we can see that the emission is being carried and then deposited right about here. These are the points at which they measured and which they took data. So you can see right about how far the lead from that emission source is getting and then depositing all along through here. So that accounts for this spike in lead. That's all coming from the source, the emission source, the plant that is going on. So it's important to understand the monitoring and the sampling methods that are going on to monitor these heavy metals. Now, we already mentioned that heavy metals such as lead create problems along roadways because cars are major emitters of a lot of these. And so this first part of the chart over here is just showing the lead content versus distance from the street. So close to the street, you have a very high content of lead. The further out you get, the more that's going to drop off. If you look at the amount in plants, then you can see that. Now notice this one is going the other direction. So 0 near the top, and then it gets higher as you go down. So very high content near the road, dropping off the further away from the road you get. Number 2 is showing mercury deposition in sediment under lakes. So what's settling out into the mud and the detritus in the bottom of a lake. And this one and number 3 kind of are indications. Again, these are all things that have happened since the industrial age. So these are not natural sources. So mercury was not something that was seen in very high levels. If we go back to sort of prehistoric and early historic times, we can see very, very low levels, stayed pretty level. You know, it was base with a slight amount of pollution as humankind sort of took off there. But you can see right about the point of industrialization. Okay, so right about when we started getting factories and industries, you can see that there was a huge jump in the amount of mercury content, and it has continued to grow since that time. Same thing if we look at cadmium concentrations. So this is a fir tree that dates back to 1800, and if you analyze the rings, you know that the rings of a tree are like little time capsules. Trees that deciduous trees that have annual growth will put on a ring for every year of growth, and depending on the size of the ring and various factors, you can learn a lot about what conditions were like sort of in the past. They're like time machines. You can see what's happened in the past. And again, if we look at cadmium levels, they stayed pretty steady until we hit industrialization here at about 1875, and then they start spiking, they go down a little, they come back up. So there's definitely an influence on this because metals are one of these things that just don't go away. They can only be changed in form. They can be tied up in different complexes or different minerals. They can be released into soil, into air, into water, but you're not going to really get rid of lead, get rid of cadmium. All you can do is try to tie it up somewhere where it's not an issue to us as human beings or to the environment, to plants and animals. So looking again at the behavior of those heavy metals, and this is, you know, the whole cadre of them here. So if we look, you can see all the different heavy metals that are being listed here. So if we look at all the factors that influence those heavy metals, it's important to understand what's influencing them, what's going to put them into solution, take them out of solution, run them through this cycle. Okay, so number 1, that's just showing the cycling of the heavy metals in the environment. Figure number 2 is showing their relative mobility based on, remember if you go back to what we looked at early on in water, pH is very important to the mobility of these elements, not only in water but in soil. Their redox potentials as well, so their ability to be reduced or oxidized to form complexes is very important to figuring out where these things are going to be in the environment. Now again, I'm not asking you to interpret that and just say what's going to be at any given point, but do be aware that if you were to carry out a study on a particular metal, then you have to understand all those influences. And I would ask you to sort of reflect on that a little bit in terms of the lab that we did. You know that we had some issues with some of the metals, and that is going to be pretty much standard for what we're able to do in a teaching lab setting. So you can see here some of the influences that may have affected the outcome of our results. So you can think about it in terms of that. And that's not saying there's anything wrong with what we did, but again, a learning experience may be very different from carrying out an actual analysis. So it's building up layer upon layer. Number 3 kind of looks at the pH dependence. So acid rain has a huge effect on the environment in so many ways, and one of the ways is what we're looking at here is the availability of these metals, whether they be metals that we need or metals that we don't want in there. So for example, if we look at silicon, aluminum, and iron, silicon, iron, even small amounts of aluminum can be micronutrients, but if you get too much of them, those can create major issues, just like we were talking about the pygmy trees with the aluminum. So you can see here that as your pH gets higher, for these 3 elements, you actually go from a higher solubility down to 0 solubility. They basically precipitate out of solution, but then as you change the pH further, you put them back into solution. So as they change their redox state and as they change their complex state. Now in number 4, we look at the solubility of 3 other metals, zinc, cadmium, and lead. Again, zinc and cadmium to an extent are micronutrients. You need a certain amount of those, but you don't want too much. So you can see here at lower pHs, those are very soluble. Those are very available in the environment, which is not necessarily a good thing. We don't want a lot of those free ions available for uptake, especially the lead. We want to tie that up. So we want to definitely keep an eye on those pH values and keep them more moderate. We don't want to let them start getting down below about 5.5, 5 or so. Now, this figure, 4.3.11, is the author talking about using extraction agents to look at the mobilization of heavy metals. Now, this is not anything that's going on in the environment. I want to make that clear. These are not environmental changes, but this is the author talking about how an environmental scientist would begin carrying out a study of any one of these. So if you want to look at metals in the environment and in particular soil, first of all, you've got to get it out of the soil. You have to use an extraction agent. Now, our extraction agent didn't work so well for us in lab. That's all right, but that means that you could try another one. So you can see the different types of extraction agents. You can see the types of binding that are going to occur. Is it going to exchange ions? Is it going to have surface absorption? So on and so forth. And then you can see the pathways that are going to occur for any of those materials that you have. Okay, you don't need to be able to recreate this plot in any way, but you do want to have a feel for, what are the extraction agents that are available and what are they useful for. So for example, if you're using electrolytes, let's say, magnesium chloride, for example, ion exchange, surface absorption, you can use it. You're not going to go much beyond that. Okay, so you can see kind of where the cutoffs are for those, how far out you can use those. So if we look back at how acid rain gets deposited in the first place, the sources of it. Remember, our emission sources are vehicles, houses, factories that are generally emitting sulfur oxides and nitrogen oxides. So that's SOx and NOx, and various ways that those can be moved around through the environment. We've talked a little bit about this, but you've got your long distance transport through clouds and winds. You can get this then rain, so wet deposition of acid rain. You get dry deposition of the gases being taken up by plants and things like that. And then you get what is known as interception depositions. And interception is where the material is taken up in the gas form by plants and by trees, which, first of all, creates issues with the nutrient levels in the plant. So when they're taking those up and it's creating acid forms within the plants, it affects their ability to absorb nutrients. It's also leading to a breakdown of the biomass that helps to remove a lot of these things from the atmosphere in the first place. So it just sort of increases the problem. And you've probably seen pictures of areas that have been deforested by acid rain. It's really, really rough on the plants. So if we look over here at this part of figure 4.3.13, it talks about acid deposition in the soil. So you have it moving through affecting decomposition. So bacteria, decomposers, humus, things that dig in the soil all get affected. That affects the minerals that are formed from that material. We do then have acids coming in to the water that's in the soil. So the stored water has a higher acid level that tends to leach out into the groundwater, so it affects the pH of the groundwater. Now, if we then take into account, keep in mind that this section is looking at heavy metals and acid rain. If we look at the effect of acid deposition on those heavy metals that are accumulated in the soil, remember that those things become more soluble, more bioavailable at lower pH, at more acidic pH. So we end up getting just a domino effect in that. We get further acidification of the soil, which can damage the inhabitants of the soil. So worms, nematodes, bacteria, anything that's in there get affected by that change in pH. We can get a direct effect by that heavy metal accumulation. You can see also the washing out of calcium and magnesium leads to nutrient deficiency, so we make those more soluble. They wash out into the leachate, into the groundwater. They're not available for things that take calcium and magnesium from the soil. Heavy metal accumulation then allows eventually a release of aluminum, which remember is toxic to plant life. So we end up getting stunted growth there, we get root damage, we get decreased resistance, we get less stability there, we inhibit the decomposition of the soil. So it has just this cascade effect throughout the whole system. Now this figure sort of takes what we talked about in the last figure and just puts it in terms of the equilibria for these different elements and metals. But basically when we look at the effects of this, so oxygen and carbon dioxide coming into the soil, CO2 being taken up by plants and O2 coming out, we can see how these minerals with just basic dry deposition, how they're going to be affected. So we're leaching out most of our minerals into our groundwater. We end up getting a lot of things added that way, ending up being discharged into a groundwater system. In turn, that increases the hydrogen or hydronium ion concentration in our soil as we continue this leaching, which remember, this is what is defined as acid. So we continue that acidification process. Now we skipped over figure 4.3.15. I didn't want you to think you'd missed it or it was left out or anything. That one is specific to types of forest in Germany, and I didn't think we needed to mention that as long as we have already mentioned you're aware of the effects of acid rain and heavy metals on plants. So it does lead to deforestation. In the next figure, though, in 16, the author looks at the effects of acid rain, in particular on one building in Europe, the Cologne Cathedral, which has been a classic case. It's made of many, many different materials. So you can see here it's been built over hundreds of years. So the period between 1248 and 1560, the material they use crumbles slowly. That's an average risk of destruction for that material. You can see here. So materials there don't tend to be affected as much by acid rain, but then they started using sandstone. So you can see the portion of the cathedral that was added onto there that's made of sandstone. Sandstone is in particular susceptible to acid rain, which we'll look at in just a second. So you can see here limestone as well. Limestone is very susceptible to that material. So you can see these areas that are the darker orange and then the paler material here in the buttresses and whatnot are all at risk. And so the government has spent a lot of money. The German government has spent a lot of money preserving and repairing this cathedral, just because of the choice of materials and then the effects of acid rain on those materials. So at the time it was being built, these were considered very strong, sturdy materials that would stand the test of time. Now we know that weathering has had quite an adverse effect. Likewise, here's another European statue. This is sort of a classic example of the effects of acid rain on these building materials and on these mineral materials. So the picture on the left here of the statue was taken in 1908, and then the picture on the right is the same statue, but now this picture was taken in 1968. So a 60-year difference. 60 years. And you can see the effects that acid rain and weathering have had on that statue. And a lot of areas of Europe have a much larger problem with acid rain than we do here in our particular area of the US. There are areas of the US that have a bigger problem, but in Europe in particular, it's a very high concentration of people, not a lot of ways to mitigate the amount of material that's being put out, so they have had issues with that acid rain. Typically, just to put it in perspective, rainwater typically will absorb CO2, so it does tend to be a little acidic. So it will be somewhere around maybe 5.8 or so just from the acidification from rainwater. Well, you start adding in all these other effects, and you can get water that's down to a pH of 4, 4.5. In some places, it's as low as below 3, like 2.6, 2.7. So it's a major issue. And what's going on? Okay, remember we talked about SOx and NOx. Well, in particular, the sulfur. Sulfur dioxide mixes with water in the atmosphere and it makes sulfurous acid. Okay. And then sulfur trioxide combines with water to form sulfuric acid. Okay. And so these acids have an effect in and of themselves. The sulfuric acid reacts with limestone to create calcium sulfate, which is soluble, and carbonic acid. So carbonic acid, remember, is essentially carbon dioxide gas and water, but calcium sulfate is soluble. So the limestone, the calcium carbonate, which is not soluble in just water, converts to calcium sulfate, which is soluble in water, and so the limestone slowly begins to crumble away, and you see these effects that you have here. So this is just an overview of acid rain and metals in the environment. So the focus is on the soil, but we can't look at it just as soil alone. We have to look at it in terms of its interplay with the entire atmosphere. Okay. So there's the first part, or the section 4.3 in a nutshell.